Here on the left, we see the bonding model of an intrinsic semiconductor, silicon again. With the addition of impurity atoms during the manufacture of the semiconductor, we can reduce its resistance. This is done in one of two ways. By doping with a group 5 impurity atom, such as arsenic as shown here, we end up with an extra electron. The energy level of this fifth electron is within the band gap, just below the conduction band. The energy levels associated with the extra electrons are known as donor levels. Even at room temperature, most of these electrons will gain enough energy to jump into the conduction band, thus reducing the resistance of the semiconductor. We call this an N-type semiconductor since the majority of conduction is due to the negative electrons within the conduction band. Remember that we previously discussed the heating of an intrinsic semiconductor. For each electron which jumped from the valence band to the conduction band, there was one hole left behind in the valence band. This meant that in an intrinsic semiconductor, electrons and holes exist in equal number. When we dope the semiconductor, however, this is no longer the case. In an N-type semiconductor, the majority charge carriers are electrons, and holes, which are still present due to the process described earlier, will be very much in the minority. Despite the majority charge carriers being negative electrons, an N-type semiconductor is still electrically neutral, since the impurity atom, arsenic in this case, will have an equal number of electrons and protons. Now let's look at the P-type semiconductors. This time the impurity atom or dopant is from group 3, so only 3 outer electrons are available for bonding with the surrounding silicon atoms. This results in a positive hole, as shown. The impurity atom in the diagram, in case you were wondering, is indium. The addition of group 3 impurity atoms leads to additional energy levels in the band gap, just above the valence band. These are known as acceptor levels. Electrons in the valence band require very little energy to move to the acceptor levels, leaving behind holes in the valence band. This is where P-type semiconductors get their name, because the majority charge carriers are positive holes. Conduction in a P-type semiconductor is due to the motion of these positive holes within the valence band. Again, P-type semiconductors are electrically neutral, since the impurity atoms have an equal number of electrons and protons. So, that's us for now.